Hello, today we'll talk about UV spectroscopy. This is another widely used method used in different disciplines of research in bioorganic chemistry, biochemistry, pharmaceutics, and industrial chemistry in different fields of research. Today, this method is very efficiently used. Here we go. Okay, UV This spectroscopy stands for ultraviolet plus visible spectrum. UV visible spectroscopy is a widely used analytical technique that measures the absorption or transmittance of ultraviolet and visible light by sample. As we talked, it measures the absorption. After the absorption, some amount of the light transmits, and that light is identified, detected based on the level of absorption is detected. So the mechanism of this method is based on this process. It identifies functional groups, named chromophores, and determines the concentrations of solutions, especially in pharmaceutical, biochemical, and material science fields by applying the Beer-Lambert law. In our previous lectures, we talked about Beer-Lambert law. It is about the absorption of light by a substance which is directly proportional to its concentration and the path length of the light through it. Again, it is expressed by the equation A equals eta, Greek letter, multiplied by concentration, and L length. A is absorption, eta is molar absorptivity, C is the concentration of the studied compound, L is the path length. It's essential for determining unknown concentrations using spectrometry. Okay, we talked about this figure in our previous lectures. The relevance to this topic is that visible spectrum plus some closer to the visible spectrum of the ultraviolet light is included in UV spectroscopy. It includes ultraviolet rays from 200 to 400 nanometers. Okay, this is about the visible light spectrum. What we need to understand from this message is that it starts from violet and is in red. Just to remember the sequence of these colors, okay, you can try to keep in mind Richard F. York gave battle in win, red, orange, yellow, green, blue, indigo, and violet. Here you can see the wavelength of different colors. Again, violet started from 380. In some cases, it's written 400, and red ends in 400, 740, 780 in some cases, and rarely it's written 800. So it depends on the capacity of different capacity of seeing the colors in different people. Okay, these capacities differs. That's why okay, here we can see some discrepancies, but it's not very significant. Okay, next. Here we can see the linkage between the wavelength, frequency, and photon energy of different visible spectrum colors. Violet has the smallest wavelength and highest frequency and highest photon energy. So we can keep in mind that the wavelength and photon energy are reversely proportional to each other. The smaller wavelength and the higher photon energy, the smaller wavelength, the higher frequency. Here we can see 380 to 450, and here the frequency differs from 670 to 790, and here we can see the wavelength of the red color ranges from 625 to 700. Yeah, and here the frequency is about 400 to 480. So here between the wavelength and frequency, we see reverse relationship. And likely here we can see reverse proportions between the wavelength and photon energy as well. The smaller wavelength, the higher photon energy, the higher wavelength, the smaller photon energy. Okay, and this is about the frequency. Hertz is the unit of frequency, which is equal to 1 cycle per second. It is abbreviated as H. Z. I would like you to pay attention to similar colors. The violet color has the highest frequency again, and the red color has the smallest frequency as shown here. And the frequency of the visible spectrum is very high. Here you can see it differs from 400 to 790 terahertz compared to the range of audible range. They are okay, 100,000 times, approximately 100,000 times bigger value. This is the audible range that the human can hear, differing from 20 hertz to 20 kilohertz, which means okay, from 20 to 20,000 hertz. Okay. And this is about the photon energy. Photon energy is the energy carried by a single photon. I'd like you to pay attention to the lowering value of photon energy from violet to red. The photon energy of the violet is between 3.26 to 2.75 eV, electron volt, and here we can see, I'm sorry, here we can see it is between 1.98 to 1.65 in red color. Okay, a photon is a fundamental particle representing a quantum of light or electromagnetic radiation. The energy of a photon is not constant, as we talked earlier. It is directly proportional to its frequency and inversely proportional to its wavelength. Photon is the fundamental reason why different types of electromagnetic radiation, including radio waves, visible light, X-rays, interact with matter in completely different ways. The energy of a photon determines what it can do. Now we are going to understand the meaning of this text in the next pages. Photon energy is expressed by this equation, E equals hv. Here E is photon energy, H Planck's constant, and V is the frequency of that spectrum of the electromagnetic wave. Again, the higher frequency, the higher photon energy. This is why violet photons are more energetic compared to red photons, as shown here. Again, we talked about this: red, orange, yellow, green, and indigo, blue, and violet. Again, sometimes the indigo is written as blue, and I mean the blue is true. Indigo is. I'm sorry. Indigo is sometimes written as blue, and this blue color that we call light blue is written cyan with colors not only in English but also in other languages. There are some, let's say, different approaches. Uh, that's why we need to keep in mind this, let's say, different groups as well. Okay. Now we are going to understand why different electromagnetic waves have kind of different heating features. Uh, this table is about heat features of electromagnetic waves based on their wavelength. Now we are going to compare microwaves, infrared, and red light. Photon energy in microwaves is the lowest among these three different types of electromagnetic waves, because microwaves has the highest wavelength. As we talked, the smaller wavelength, the higher photon energy, the higher wavelength, the smaller photon energy. Infrared is obviously of medium level of photon energy, and the red light has the highest photon energy compared to microwaves and infrared. And based on this, they have different heat features as well. But there is another point that we have to pay our attention to, that microwaves usually target whole molecules, and the infrared targets chemical bonds within molecules, and the red light targets electrons in atoms. Based on this comparison, we can understand that the visible light and some higher electromagnetic spectrum of ultraviolet targets electrons as well. Again, microwaves target whole molecules, infrared targets chemical bonds within molecules, and red light or visible light targets electrons in atoms. And this is the reason of UVV's spectroscopy, and we are going to understand in the next pages the meaning of this comparison. And this is about heating mechanism. Microwaves cause rotational excitation of the molecules. Infrared causes vibrational excitation, and red light causes electronic excitations, which means electrons jump from the constant state to excited state in atoms. And this is about heating depth. Microwaves penetrates and heats internally. Infrared heats the surface, and red light heats the surface as well, but absorbed very quickly. And based on these properties, again, in real world, microwaves are used in microwave oven, and the infrared is used in toast heating lamps, and red light is used in old incandescent bulbs, but those bulbs have infrared lights as well. Okay, And now we are going to understand the meaning of this topic. This is about what is light absorption. Light absorption is the process in which light is absorbed by matter and converted into energy. In an atom, electrons vibrate at a specific frequency. This is called the natural frequency. If a wave of light hits a material in which the electrons are vibrating at the same frequency as the wave of light, the electrons will absorb the energy and convert it into vibrational motion. This is why objects have different colors, different materials. Electrons will vibrate at different rates and therefore absorb different frequencies of light. Here we can understand that as the light reaches the electrons, they cause the electrons to have higher energy, and they jump into excited state as shown here, which is far from the nucleus compared to the constant state. And at this state, electrons cannot be held long, and they tend to return to their constant state. When they are returning to their state, okay, some energy that were absorbed by the electrons to jump will be released as well. Here we can see, okay, this line can be understood as the ground state or constant state, and based on the photon energy of the electrons, I mean photon energy of the electromagnetic waves, including different colors, the jumping, let's say, state of electrons might differ, since red color have a very lower energy. It might cause the electrons to jump to closer state, and blue color might cause the electrons to jump to far the farthest distance as indicated here. Electrons can only exist in discrete energy levels. This can also be called electron shells. We know about it. They can't exist halfway between. Okay, you know what I mean. You know what it stands for. Uh, if this is the state, okay, they cannot be here or here. The lowest energy level that an electron can be in is called the ground state, as we talked here. For an electron to move from a lower energy level to a higher energy level, it must absorb a set of amount of energy, because energy levels are quantized. We talked about this. This means that the energy absorbed by the electron must be exactly the same as the energy difference between the two levels. Yeah, in this case, I try to deliver that message. The level of energy absorbed here and released here are expected to be the same. Okay, when an electron absorbs energy, is it promoted to a higher energy level further away from the nucleus of the atom and is described as being excited. So these states of electrons are the excited status. The energy level that is absorbed when the electrons are jumping from here to here or from here to here are released when they are returning to their ground state. Okay, that's why the energy absorbed and the energy released are expected to be the same. Okay, next. And this is about what happens after an electron becomes excited. Now we are going to come closer to the topic. Why we need to understand all these things can be understood here. And this is about the, let's say, spectrum of the electromagnetic waves. It can be here as well. Here we see only the visible spectrum, and ultraviolet from 200 to 400 nanometers are also included in UV with spectroscopy. Some short, let's say, uh, ranges of the electromagnetic waves are absorbed. In this case, here we can see the absorption are absorbed by different atoms as indicated here. Based on that, okay, it is possible to identify the atoms as indicated here. For example, this absorption belongs to oxygen, this absorption belongs to hydrogen. Hydrogen is the smallest atom as we know. That's why, okay, here we can see a kind of short and primitive, let's say, uh, absorption spectra compared to other atoms shown here, which have more electron shells and greater number of electrons. Electrons don't like being in an excited state. We talked about this. This means that after becoming excited and moving to a higher energy level, they soon fall back to their original level. However, to do this, they have to release a packet of energy. This is called a photon. The size of photon released is exactly equal to the size of the jump the electron had to make in the first place. Okay, this means okay the absorption of some ranges of electrons equals the emissions as shown here, as explained here, uh, because the electrons can absorb the exact, let's say, in short range of this, let's say, orange color in this case, while they are jumping from one state to another. And reversely, when they are falling back, okay, the same amount, I mean, the same range and the same amount of the energy is released. The meaning of this text can be understood based on this absorption and emission spectra. Okay, and this is about absorption spectroscopy. Absorption spectroscopy is a technique used to measure the absorption of energy. The absorption spectrum of a certain material is shown by a continuous band of color with black lines between them. The colored parts represent the total light that is focused on the material. The black lines show an absence of this light. These are the parts of the spectrum where the electrons have absorbed the light photons. And there are two types of absorption spectroscopy. They can be atomic or molecular. Atomic absorption spectroscopy is the method of producing a spectrum when three atoms absorb different wavelengths of light. This is usually used for gases. Uh, Here we witnessed it in the previous page. We witnessed the absorption spectra of four different atoms: sodium, nitrogen, hydrogen, and oxygen. Uh, and the second type, molecular absorption spectroscopy, is the method of producing a spectrum when the whole molecules absorb different wavelengths of light, usually ultraviolet. Some closer to the ultraviolet range of visible spectrum can be used more often, but in UV visible spectroscopy, the range around red, orange, or yellow is not very kind of high significance as of ultraviolet or violet blue colors. Okay, and this is about the emission spectroscopy. Emission spectroscopy is used to measure the photons released when an electron falls to a lower energy level. after becoming excited. The emission spectrum of a certain material is shown by a black band with separated colored lines. Here we can see uh, the absorption. Okay, I apologize for the figure. It could be different. I mean, this is the absorption figure, and in emission, it could be like this. I want you to understand the differences in absorption and emission spectrum. And this is about the emission spectroscopy. The emission spectrum of a certain material is shown by a black band with separated colored lines. These color lines are the parts of the spectrum where photons have been released from the electrons when they fall to a lower energy level. Okay, and there are two types of emission spectroscopy as well, line and continuous. When the spectrum is shown as lots of lines separated by black spaces, it's a line emission spectrum. When the spectrum is shown as lots of colors in one particular wavelength, it's a continuous emission spectrum. Emission spectroscopy is used to identify a substance because of the energy released when the electrons fall back to their ground state is different for every substance. We talked about this. If you find this topic a bit complex, I recommend you to watch it video again or some parts of the video again so that you might catch the meaning. And here we can see a continuous spectrum. This one is a continuous spectrum. This is absorption spectrum for hydrogen. This is emission spectrum of hydrogen. And a continuous spectrum holds all wavelengths of light across a certain wavelength range. As its name implies, it is uninterrupted with no gaps or intensely bright bands as shown here. The hot compact point of light emitted by stars is nearly a continuous spectrum, and based on some differences, intensities of some electromagnetic wave ranges, it is possible to identify what kind of elements exist in the sun, and that the presence of hydrogen and helium is identified based on the spectrum, light spectrum of the sunlight. And let's watch these videos based on these kind of, let's say, absorption spectrum as indicated here. It is possible to find out about the presence of atoms or mixture of atoms. So the spectrum can be identified based on this kind of, let's say, peaks or based on this kind of spectrum. Okay, next. And now we are going to understand about the utilization of the UV visible spectrum. And this is about analysis of chemical substances. One of the primary applications of UV visible spectrophotometers is the analysis of chemical substances. Is it possible to identify the chemical compound based on UV-Vis? No, it's impossible, but it is possible to suggest about the chromophore groups, about some, let's say, similar spectrum that could be found in compounds like those studied samples. By measuring the absorption spectra of compounds, scientists can identify and quantify unknown substances in various samples. This identifying does not mean the complete meaning. It means identifying based on some functional groups, let's say. UV visible spectrophotometry is particularly useful for analyzing the concentration of chromophores, which are compounds that absorb light at specific wavelengths. This technique is widely employed in pharmaceutical, environmental, and industrial laboratories. And is it possible to use UV spectrophotometry for quantification? Yes. The answer is yes. UV spectrophotometry enables quantitative analysis by determining the concentration of a compound in a sample. This can be achieved by measuring the absorbance of a known standard solution and creating a calibration curve. In our colorimetry analysis, we talked to you about the calibration curves. I recommend you to watch that video as well. By comparing the absorbance of an unknown sample to the calibration curve, the concentration can be accurately determined. This method is widely used in pharmaceutical quality control, environmental monitoring, and clinical diagnostics. Again, based on the similarity of some expected compounds and the calibration curve that was developed based on that expected compound, it is possible to identify. It's possible to quantify the compound, to quantify that compound in the given samples. Okay, and this is about the qualitative analysis. In addition to the quantitative analysis, UV spectrophotometry is also used for qualitative analysis. By studying the absorption spectra of different compounds, the scientists can identify the presence of specific functional groups or chemical bonds, as I mentioned earlier. This information is crucial for determining the chemical composition of unknown samples or verifying the purity of synthesized compounds. If some tools are used for quantification, it is possible to use them for quality analysis as well in general. And this is about the biological and biochemical research. UV spectrophotometers find extensive use in biological and biochemical research. These instruments are employed for the quantification of DNA and protein. They can be used for enzymatic activity assays and cell viability studies as well. UV spectrophotometry enables scientists to measure the absorption spectra of biological molecules, providing insight into their structure, concentration, and interactions with other compounds. Okay, and also they are used in pharmaceutical applications effectively as well. In the pharmaceutical industry, UV spectrophotometers are used heavily. They are used for drug analysis and quality control. They are used to assess the purity, concentration, the stability of pharmaceutical compounds. Again, some molecules have their own, let's say, UV absorption spectrum, and the pure compound has their, let's say, own spectrum. If we identify the spectrum, UV spectrum of the given samples, if they differ from the spectrum of the, let's say, standard, okay, we can make a conclusion about impurity of those samples as well. The meaning of the text belongs to this explanation. These instruments aid in the development and formulation of drugs by ensuring that the desired compounds are present in the correct amounts. UV spectrophotometry is also employed in dissolution testing, where it helps determine the release rate of drugs from various formulations as well. Which means, okay, as the drugs are released from the delivery systems, okay, they tend to absorb their own spectrum. Based on the changes, it is possible to find out about the release of compounds. We are going to see some exact figures and understand the meaning of this text in the next coming pages. Here we can see concentration and the changes, concentration and the intensity of absorption of this given compound. rose Bengal 4,5,6,7 tetrachloro 2,4,5,7 strain tetraiodofluorescein, and it shows this kind of small, let's say, spectrum at 5 micromolar dose. As the concentration increases to 10, 15, 20, and 25, we can see higher intensity of absorbance around 200, let's say 30, and how much? About 550, yeah, something like that. And here we can see much results and understand the efficacy of this tool and quantification. In this case, in A case, acetone extracts obtained from the flowers and leaves of Polygala major. And we can see that the flower macerated with acetone, FME, this one, the blue line, had, let's say, had higher intensity compared to FUA, flower ultrasonicated with acetone. Flower, okay, this one macerated with acetone, the light blue line, and the I don't know what color, red brown color. This belongs to a flower ultrasonicated with acetone. So based on these differences, we can make a conclusion that the concentration of compounds that have absorbance around 340 are expected to be extracted with lower efficacy when they are ultrasonicated with acetone, as shown here. When they are macerated with acetone, the percentage of those compounds to be extracted is expected to be higher. Okay, this is the meaning. This is the possibility how we can effectively use ultraviolet visible spectroscopy. And here we can see, let's say, similar tendency with left macerated with acetone and left ultrasonicated with acetone. Left macerated with acetone had higher efficacy and to extract those compounds having absorbance at this range compared to those that were ultrasonicated with acetone as well. And in this case, okay, we can see, okay, B1. Flour macerated with ethanol. Okay, this is with methanol, FMM. Yeah. Uh, I mean, in this case, I didn't find this color. Maybe it was my mistake. I don't know. Now I noticed it. In this case, okay, in B case, so given here, flowers macerated with methanol and flowers ultrasonicated with methanol did not have some higher differences compared to those carried out with acetone. I mean, the green color and violet color that belongs to left macerated with methanol and left ultrasonicated with methanol did not have the big differences here, you can see. Yeah. Or here we can see even more non-significant differences between flour macerated with methanol and flour ultrasonicated with methanol samples. This means, okay, based on UV visible spectroscopy, we can identify the efficacy of extraction methods as well. Next. And these two compounds differing from each other based on the number of carbon that this functional group was linked to, had this kind of UV spectrum. Yeah, and the monomer of this compound had this kind of UV spectrum with the peak around, let's say, 340, 345. Yeah, as this compound forms dimers, trimers, or tetramers, or pentamers, here we can see the shift of the peak and absorbance towards the visible spectrum. Yeah. In monomers, the peak belongs to 345, something like that. And in pentamers, here we can see this line, or in tetramers, between pentamers and tetramers, there's no big difference. In tetramers and pentamers, the peak belongs to some ranges around 480, let's say, yeah, 475, something like that. So from these results, we can understand that we can also find out about the shifts of different compounds, shifts of absorbance of different compounds, UV visible spectrum that can differ based on their monomers or polymers. And similar tendency were observed with this compound as well. So this is about the differences of UV spectra, UV absorption, spectroscopy of different compounds that could differ as they form some mer dimer forms. Okay, next. And this is another example that the addition of hydroxyl group based on the positions that might change the absorbance, UV absorbance. This is under 325 UV absorbance of this compound phenol. Yeah. Okay, phenol has this kind of absorbance in some concentrations, and the addition of hydroxyl group in meta position, yeah, did not, let's say, cause big differences compared to phenol, but the addition of OH group in ortho condition, as you see, caused the intensity of the absorbance to be much higher compared to phenol. And also the peak shifted, let's say, from around 260 to 275. Yeah. And the addition of a hydroxyl group in para condition, as you see, lower the intensity of the absorbance, not only lower, but also shifted from 275 to 200, let's say 90, yeah? Something like that. And this compound that does not have OH, instead of OH, it has these carbonyl groups linked to the benzene ring. I had the peak at let's say 240 nanometers. So based on the functional groups here, we can see that the peak of the compounds and the absorbance levels of the ultraviolet or visible spectrum can differ from each other. Okay, next. And this is about UV absorbance spectra of phenol as a function of photodegradation. Photodegradation of phenol was studied as shown in this case, I'd like you to pay your attention to the peak of this blue line, yeah, at 0 degree, I mean 0 point of phenol. It has the highest, let's say, peak at around 200, I don't know, 240, I mean 270, 70, something like that, yeah. Yeah, 270. And as time goes by from 0 to 6 hours, yeah, 360 minutes, the peak intensity lowered from 1.5 to 0.2. Yeah, here we can see linear lowering tendency from 1.495 to 0.2. And here we can see differing, let's say, differing tendency at around 245. Yeah, something like 245 here, 245, 245 nanometers. I mean, here the at zero level at around 245. Here we can see it is somewhere, yeah, as time goes by. Here we can see some increasing tendency and then lowering. Yeah, these are the pointers that we have to pay our attention to while we are analyzing the light UV visible spectrum of compounds. So the peak is the first point. And here we can see differences as time goes by that might explain the photodegradation of phenol. Yeah, here it's coming in this tendency, and here we can see increasing pointers of this case as well at 275. Here we can see, yeah, 285, I'm sorry, yeah, 285. At 0 point, it is around 0 122, and here it is increasing, and lowering, but still the last point after 6 hours is still higher compared to the 0 point. Here we can see those results. So based on this kind of comparison, we can find out about the photodegradation as well by using UVV spectrum. Okay, next. And this is about the degradation spectra of Congo red. This is a compound that's used to make the compounds visible, to paint the compounds. Congo red at 0 point has had this kind of peak at around 500 nanometers, as it's mixed with 1% 1% zinc 2 oxide nanoparticles. We can see the lowering tendency of the peak of Congo red. Here we can see that it is smaller and smaller within 150 minutes, yeah, within 2.5 hours. And when the concentration of zinc oxide is 2%, here we can see the faster degradation of Congo red as shown here. The degradation that was used for 2.5 hours with 1% zinc oxide nanoparticles were shown for 60 minutes with 2% solution of that compound. And here we can see similar or a bit faster degradation by using 4% zinc oxide nanoparticles. So by using different approaches, we can effectively use UV visible spectroscopy for determining the concentration of compounds, degradation of compounds, about the synthesis and other useful approaches can be developed by us. And for that, we need to read and get acquainted with the contents of research papers of the last years. I recommend you to read the papers from the NCBI or Science Tract more rather than reading some papers that could be found in Google Scholar. Okay, this is all. I express my thanks to you all for your attention. And to those who watch us on YouTube, I kindly ask you to support us with your likes so the video materials can reach a wider audience. And for now, that's all. Thank you for your attention and have a good day.